Have you ever looked at pictures of orbitals and thought, why is the s orbital a perfect sphere? P orbitals look like dumbbells. D orbitals look like weird clovers or double dumbbells. And F orbitals look like abstract art gone wrong? Is it just random shapes we're forced to memorize? Or is there an actual reason behind them? Today, we'll finally make sense of S, P, D, and F orbitals, simply, visually, and logically. First, let's clear the biggest myth. Electrons do not move in fixed circular paths around the nucleus. That idea comes from the old Bohr model, useful but incomplete. In modern physics, electrons are not tiny balls following fixed paths. Electrons behave like waves, standing waves around the nucleus. And just like a guitar string can only vibrate in certain patterns, one node, two nodes, etc., electrons can only exist in certain allowed wave patterns. These allowed patterns are what we call orbitals. Now, why don't all orbitals look the same? The answer lies in two words: angular momentum. In quantum mechanics, we give this a number called L, and this number decides the shape. Let's start with the simplest one, s orbital. The s orbital is spherical. Why? Because the electron wave spreads equally in all directions from the nucleus. No preferred direction, no angular complexity. So value of L for s orbital is 0. That's why every s orbital is always round. The only variation is distance from the nucleus. Radial nodes of es orbitals like 1s, 2s, 3s, etc., just different in size. Simple, clean, and symmetrical. Now comes to the p orbital. The value of angular momentum for a p orbital is 1. So this creates two regions of high probability with a node, a zero probability region, in between. That's why p orbitals look like dumbbells. Here, the electron wave has directional behavior. Instead of spreading evenly, the wave oscillates along an axis, and because space has three directions, p orbital has a px, py, and pz orbital. Same shape with different orientations. Now things get more interesting. D orbitals. Angular momentum for d orbital is 2, and it allows 5 independent ways to arrange those two nodal planes. So we get 5 d orbitals. Instead of 2 lobes, most d orbitals have 4 lobes. Orbital dxy, dxz, dyz, dx squared minus y is squared look like 4-leaf clover, while dz squared is a bit different. Looks like a donut around a double dumbbell. And finally, f orbitals. These are the most complex ones. Angular momentum value is 3 for f orbital. There are 7 possible f orbitals, usually 8 lobes or more exotic shapes. Multiple nodes, multiple lobes, very intricate wave patterns. That's why f orbitals look intimidating, but they're just advanced wave shapes, nothing more. So why do orbitals have these shapes? Because electrons are standing waves, and standing waves around the nucleus can only exist in very specific patterns, patterns that match whole number units of angular momentum. Hence, shapes of orbitals are neither arbitrary drawings nor magic, just wave rules in 3D space. If orbitals finally make sense now, hit that like button. Your brain earned it. Subscribe for more visual physics and chemistry that actually makes sense. And remember, the atom is way weirder and cooler than it looks.